Welcome aboard. My name is Jim Cook, and I'm going to be the instructor for this segment. We're going to be talking about why sailboats go upwind. Now, I have to tell you, this is something that confused me since I was a very, very, very little boy. I'd be sitting in my bathtub, and I could blow on my little boat, and I could get it to go down to the other end of the bathtub. But in order to get it to come back, I had to go to the other end of the bathtub and blow it in the other direction. And I remember when I was in first year university, I had a friend who had a cabin on a lake. And we went out to his cabin, and we could see the boats sailing out on the lake. They were involved in a race. And I said to him, "So, what's going on here?" And this friend supposedly knew how to sail. So I said to him, "Well, what's going on? The wind is blowing from this direction, but the boats are going in this direction. Is there a wind pattern out there that is blowing in one way down the lake and then blowing the other way back so that the boats can go to the other end of the lake?" And he said, no, the boats are just sailing upwind. And I was, wow, how do the boats sail upwind? And he supposedly knew how to sail, and he said, well, they just tack their way upwind. I have to tell you, that meant absolutely nothing to me. So in this segment, we're going to show you the physics of how and why boats sail upwind. We're going to start with a bit of historical information. This is a picture of a square rigger, and these boats could sail upwind a little bit, up to 70 or 80 degrees off the wind, but they were very, very inefficient. This is why we have trade winds and trade routes. These boats needed to sail downwind, and so they would find places in the world where the winds habitually blew in the direction they wanted to go, and that is the route that they would take to carry their cargo. Even an average modern sailboat can get up to within 40-45 degrees of the wind. So in the late 1800s, early 1900s, we started having triangular sails on our boats, and these triangular sails are what make it possible for the boats to sail upwind. It is not uncommon for boats to be able to sail 40 to 45 degrees from the eye of the wind. America's Cup boats sail a whole lot closer. I'm not sure exactly what the current technology is doing with these new wings that they're using, but you can absolutely, even in previous generations of America's Cup boats, get it up to within about 25 degrees of the eye of the wind. So we're going to look at the wind, and we're going to think of the wind as being made up of millions and billions of particles. So it is July the 4th or Memorial Day or some day that we're having a parade at our hometown, and each of these lines represents a line of musicians in the parade. When they get to the corner, the guys on the inside basically stand still and stomp their feet while the guys on the outside step faster, and the band or the parade wheels around the corner. So if we think of the wind as being made up of millions and billions of particles, if we look at a certain area of the wind and we compare the number of particles per area, we can see that area A would be a low pressure area and area B would be a high pressure area. So the tendency would be for an object to move from the high pressure area towards the low pressure area. Now let's move on and take a look at the wind going over the top of an airplane wing. The wind coming over the top has further to go than the wind coming under the bottom, and therefore the distance between the particles gets further apart as the wind is going over the top, and we create a low pressure area that actually lifts the wing up into the air and the airplane attached to it. I have to admit, when I get on an airplane and I look out at those stubby little wings, it tests my imagination that this plane carrying all these people, all the fuel, all the way to the airplane, and all the luggage and everything else is actually going to get off the ground. But we all know it does, and it's the wind going over the top of the airfoil creates a low pressure area and actually sucks the airplane up into the air. So now we're going to watch a short video that is going to demonstrate how the faster flow of air over the top of a curve will create suction. There's a really simple and easy way to demonstrate the faster air going over the top of a curved surface, how it will create lift. Take a piece of paper, any sheet of paper, hold it by the edges, and then put up to your mouth. And you can see when I put it up to my mouth that my mouth is very much on top of the piece of paper, and then blow. You see how the piece of paper came up? You can see that my mouth is very much above the piece of paper. Now, try it underneath. Separate your hands, put your mouth below the piece of paper, and blow the same way. You can see there is significantly less force. Blowing above the piece of paper creates a lot more lift than blowing underneath the piece of paper. The wind going over the top of the curve is going faster than the wind underneath the piece of paper, and therefore you get lift. A classic example how the faster moving air creates a low pressure system which sucks the piece of paper up. Okay, let's back up for just a second and let's talk about vectors. So we're going to do a vector analysis of how a boat sails upwind. And in order to do a vector analysis, we have to all understand what vectors are. A vector is a graphical representation of a force. So if you push an object from left to right, so we've got an object here, and we push it from left to right, we can draw that force as an arrow. If we only push the object half as far, then the arrow would be half as long. Same thing if we raise the object up. If we had an object here and we raise it up, then the vertical force could be represented by a vector pointing straight up. Now, what would happen to the object if you applied both forces at precisely the same time? The way we add vectors is we take them and we join them head to tail, and then we join the origin to the finishing point, and this green vector would be what we call the resultant vector. So let's do a vector analysis of what happens with a sailboat. So here we have a picture of a boat. The wind is coming from the top of the slide, and you have to be careful. The wind does not always come from the top of the slide. So the wind going around the outside of the sail is creating a low pressure, which is actually sucking the sail and the boat underneath it in this direction. As the boat is being sucked in this direction, the keel at the bottom of the boat resists being dragged sideways through the water. And the resistance to go in one direction, we can draw as a pull in the opposite direction. Now, if you don't believe this, get somebody else and ask them to hold hands. Tell them you want them to pull towards them, and I want you to resist them pulling. As you resist them pulling, are you not pulling in the opposite direction? And the answer is yes. So we can draw the resistance to be pulled in one direction as a pull in the opposite direction. And that's what I've done here. The resistance of the keel to be dragged sideways through the water in this direction, we have drawn as an arrow in the opposite direction. So now we have to add these two vectors. The red vector represents the pull of the sail. The blue vector represents the resistance of the keel. And the green vector represents the boat going upwind. Now notice it's going upwind at an angle that is about 45 degrees to the wind. So there's the wind. This is a little greater than 45 degrees, but that angle is critical. You cannot sail directly upwind, and we'll talk about that in a second, but you can sail at an angle of about 45 degrees. So this is the wind coming over the port side of the boat. So the wind's coming over the port side of the boat, and we call that being on a port tack. And we'll talk about that a little bit later. Now here is a boat on a starboard tack. So the wind is now coming over the starboard side of the boat. The wind coming around the outside of the sail is creating a low pressure area, pulling the boat in that direction. The keel is resisting again. Again, we take the vectors, we add them together, and we get the green vector with the boat going upwind. So here is the situation. Boat A is down here at the bottom of the screen. Boat B is at the top. So boat A sailed along and then did a tack and started off in the other direction. Question, is boat B further upwind than boat A? Yes or no? And obviously the answer is yes. So the boat is actually sailing upwind. Now there are three positions of the sail relative to the wind. Notice that only one of them is proper. The first one on the left here, the sail is luffing, so the leading edge of the sail is pointing into the wind and the leading edge is flapping. If we were to take the end of the sail and move the end of the sail this way, then the sail would act very much like a flag. It would just, the entire sail would be flapping away in the wind, and that is not going to give us any power. The proper angle of the sail to the wind has the smooth flow of air going around the outside of the sail. And then we have stalled, where the angle of the sail, you see this angle of the sail relative to the wind, is too steep, and the wind can't stick to the contour as it goes around the sail and spills off the sail. There is one angle and only one angle of the sail relative to the wind. We have telltales that are on the leading edge of the sail. The telltales indicate if you've got the smooth flow of air going around the sail, and what you want is both telltales streaming straight back. I've drawn a red telltale for the port side of the boat and a green telltale for the starboard side. That is not necessarily the case all the time. So again, there is one angle and only one angle of the sail relative to the wind. So here we have a boat that is beating, sailing upwind as much as it can. Here we have a boat that is going across the wind. Now, notice between these two slides, I'm going to flip back and forth a little bit here. You can see that the angle of the sail to the wind is staying the same all the time. However, the angle of the sail to the boat has changed. The angle of the boat to the land has changed. The angle of the boat to the wind has changed. But the angle of the sail to the wind has not changed. And here's a boat going downwind. Again, the angle of the sail to the wind has stayed the same. So the angle of the sail to the wind stays the same. The angle of the boat to the land changes. The angle of the boat to the wind changes. The angle of the sail to the boat changes. But the angle of the sail to the wind stays the same all the time. So in summary, it's a smooth flow of air going around the sails that creates a low pressure area that in essence pulls the boat to weather. I hope this has been of some help. At eLearn to Sail, we offer the following classes via webinar. We teach Weather for the Mariner, Coastal Navigation, and Celestial Navigation. Happy sailing. Thanks very much. Bye.